Hello everyone. Today we are going to talk about MotionLM, multi-agent motion forecasting as language modeling. The motivation for this research is rooted in the need for improved performance in the representation of multimodal future distribution. Existing approaches have struggled to adequately capture the joint distribution over multimodal futures, which is a critical aspect of interactive motion forecasting. The limitations of these existing approaches lie in their inability to fully represent the diversity of multimodal future behavior. They often rely on trajectory anchors or static intention points, which may not fully capture the complexity and variability of real-world motion. To address these limitations, this research introduces a novel method that leverages multi-agent rollouts over discrete motion tokens. This method allows for a more comprehensive and accurate representation of the joint distribution over multimodal futures, thereby improving the performance of interactive motion forecasting. The approach details involve generating a sufficient number of samples or rollouts from the model. These rollouts are then clustered down to a limited number of modes for evaluation. The model is trained on the WOMD Interactive Prediction Challenge dataset, a benchmark task that requires a compact representation of the joint future distribution. The reason why existing approaches are not good enough is that they do not adequately capture the diversity of multimodal future behavior. They often rely on trajectory anchors or static intention points, which may not fully capture the complexity and variability of real-world motion. This research aims to address these limitations and improve upon the state-of-the-art in interactive motion forecasting. The authors of this paper are addressing the challenge of interactive motion forecasting. This problem is significant as it involves capturing the joint distribution over multimodal futures, a task that existing methods may not adequately perform. The authors identified that previous approaches often relied on trajectory anchors or static intention points, which may not fully capture the diversity of multimodal future behavior. To improve upon this, the authors introduced a method that leverages multi-agent rollouts over discrete motion tokens. This approach allows for a more comprehensive representation of the joint future distribution. The authors also implemented a non-maximum suppression (NMS) aggregation scheme to uncover the underlying modes of the distribution and estimate the probability of each mode. The author's method has shown promising results, establishing new state-of-the-art performance on the WOMD Interactive Prediction Challenge. This achievement indicates that their approach to interactive motion forecasting is a significant improvement over existing models. In addition to this, the authors have identified potential avenues for future work. These include leveraging the trained model in model-based planning frameworks, exploring distillation strategies from large autoregressive teachers, and deploying faster student models in latency-critical settings. These future directions suggest that the author's method not only addresses current challenges, but also opens up new possibilities for further advancements in the field. Section 1. Problem formulation and approach. The authors address the challenge of interactive motion forecasting, aiming to improve the representation of multimodal future distribution. They approach this problem by leveraging multi-agent rollouts over discrete motion tokens, which is a novel method that differs from previous approaches. This method allows for a more accurate capture of the joint distribution over multimodal futures. Section 2. Method design and experimentation. The authors designed a method that generates a sufficient number of samples or rollouts from the model. These rollouts are then clustered down to a manageable number of modes for evaluation. The model is trained on the WOMD Interactive Prediction Challenge dataset, and its performance is evaluated across varying interactive attention frequencies and numbers of rollouts. The authors also conducted an ablation study to understand the impact of different model parameters on performance. Section 3. Improvements and innovations. The proposed method establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge, surpassing the previous top entry. The model's performance improves with additional rollouts, indicating the effectiveness of the proposed method. The authors also introduced a novel way of using the model in model-based planning frameworks and in latency-critical settings. Future work includes exploring distillation strategies from large autoregressive teachers, which could further enhance the model's performance. Technical results. The proposed model demonstrates superior performance in the WOMD Interactive Prediction Challenge, establishing a new benchmark in the field. The model outperforms the previous top entry on joint map with just 32 rollouts, indicating its efficiency and effectiveness. The model also shows a significant improvement in miss rate over all prior works, with a relative 9% reduction compared to the previous state of the art. In the Interactive Prediction Challenge on WOMD, the model achieves a 6% relative improvement in map and 3% relative improvement in miss rate over the previous top. Scoring entry. Implications of results. The results imply that the proposed model is highly effective in interactive motion forecasting, outperforming existing models in key metrics. The improvement in miss rate suggests that the model is more accurate in its predictions, reducing the likelihood of errors. The model's success in the Interactive Prediction Challenge indicates its potential for practical application in real-world scenarios. Ablation studies and results. An ablation study was conducted to evaluate the performance of models with different numbers of parameters. It was found that a model with 27 M parameters overfits while a model with 300K parameters underfits. Both the 1M and 9M models perform decently, suggesting that there is a balance to be struck between model complexity and performance. Implications of ablation studies. The ablation study results indicate that model complexity, as measured by the number of parameters, can significantly impact performance. Overfitting and underfitting are potential issues that need to be carefully managed in model design and training. The decent performance of the 1M and 9M models suggests that these may be optimal parameter sizes for this type of forecasting task. Key highlights. 1. Key insights. The paper introduces a novel method for interactive motion forecasting that surpasses existing models. The performance of the model improves with the addition of more rollouts. The model can be utilized in model-based planning frameworks and in latency-critical settings. Future work will explore distillation strategies from large autoregressive teachers. 2. Key contribution. The paper presents a method for interactive motion forecasting that leverages multi-agent rollouts over discrete motion tokens. This approach captures the joint distribution over multimodal futures, addressing limitations of existing methods. 3. Key idea. The core concept of the paper is to generate a sufficient number of samples, rollouts, from the model, which are then clustered down to k equals 6 modes for evaluation. The model uses 512 rollouts per replica for final leaderboard results. 4. Key results. The model surpasses the previous top entry on joint map with just 32 rollouts. It establishes new state-of-the-art performance on the WOMD Interactive Prediction Challenge. A model with 27 M parameters overfits while 300K underfits. Both the 1M and 9M models perform decently. The main results use 9M parameter replicas. 5. Key conclusion. The proposed model has set a new benchmark in the WOMD Interactive Prediction Challenge. Future work will focus on leveraging the trained model in model-based planning frameworks, forming a search tree over the multi-agent action rollouts, and learning amortized value functions from large datasets of scene rollouts. Additionally, distillation strategies from large autoregressive teachers will be explored to enable faster student models to be deployed in latency-critical settings.